Welcome back. Now, we have looked at number 1 the Lennard-Jones potentials, and then we looked at the problems with their application into systems like metals. We also talked about EAM potential, where we said we can use the embedding energy as well as the repulsion energy and calculate accurately the face centered cubic metals and how they behave, and including their behavior with elastic constants and their relationship with the Cauchy equality. So, with that understanding, now let us move on to larger molecules. So, we looked at molecules which were smaller ones, and we also look at the krypton, xenon, argon, and they were very simplistic ideal gases. But now we are looking at hydrocarbon chains, very long chains. They have different kinds of twist and torsions. There are different angles. There is angular relationship between different atoms in the hydrocarbon chain. There are different radicals connected to it, which make up for the protein structure. Some of the biological applications, which you will see some of them later on, like the protein folding. As you know, protein is a very complex substance which is responsible for the life in human beings. Every part of body requires certain kind of amino acids, which are all put together in 22 different kinds of proteins. So, all of that biological understanding, including the base pairs in a DNA, which are almost like 3 billion base pairs, we are now going to look into some of those systems from the molecular dynamics perspective. One of the great application which is used quite a bit in commerce today is the discovery of new drugs for different kinds of diseases, and molecular dynamics is used quite a bit, and what we also sometimes call molecular mechanics, where you can formulate new atoms and new molecules and see how they attack different enzymes and different kinds of biological system in your body, especially if there are some bacteria or other disease cells are growing in your body, and if you have to destroy them using some of the chemical bonding. Then in your blood, and it has to go through the bloodstream, and then it has to go to the right location. It is a highly complex system, and that is where a lot of effort and money and funding is put into creation of the drugs. Almost $1 billion is spent on the discovery of the drug, to the point it shows up in the market, and you are able to then get the prescription from your doctor for some of these new drugs. So, the molecular dynamics and molecular mechanics and Monte Carlo is almost required tool for these kinds of situation, because there are so many possibilities in molecular system, very large. So, for you to eliminate those possibilities, you have to do computational experiments. If you have to do in a brute force method real experiments, you will spend probably, instead of $1 billion, you may spend $5 billion, because you have to just do it by brute force. But by doing computational experiments, now you can eliminate possibilities to 30 experiments as compared to 3,000 experiments that you have to consider. And that is the beauty of this whole model. So, now we want to look at using our molecular dynamic simulation system for the bonded potential models, where there are large chains and they have different kinds of configurations. So, if you look at this slide on your screen, you look at the molecules have bonds, and these bonds are of different kinds. Valence bonds, there are electronic bonds, and there are also very much very highly specialized hydrogen bonds, which is essentially makes the life in human body possible. So, if you look at this situation, you may have 1, 2, 3 and 4. We just look at these 4 locations for the phi a particle. So, these could be 4 carbon atoms. They are connected with this carbon chain, but they are in spatial sense, they are in different angles. So, they are essentially, we are looking at the angles in the molecules. These are simple chain molecules. So, you can look at the angle between 3 and 4, which is 2, 3, 4. So, 2, 3, 4, that angle you are looking at there. So, various phi is the angle between different planes in which you work with. So, now we are looking at complex 3-dimensional system, which has all kinds of atoms connecting to it, all kinds of radicals connecting to it. And if you look at the structure of human cell, which is made out of these hydrocarbons, and if you want to destroy some of the disease cell, then you want to go into one of these carbon chains and add that new element coming from the drug element that you are adding to it, and once it adds to that cell structure, then it starts destroying it. That is how you get over your disease, because those disease cells are found, and the system is able to alter their situation and create the cell death mechanism. So, in this case, moving forward, we already had looked at in one of the first lectures that intramolecular interaction happens between the atoms that are connected together. So, if you look at Rij and the equilibrium radius between the atoms, those are two ideas. So, in case of these molecules which are longer chain molecules, you start with an equilibrium structure, and you know Monte Carlo could be a great method to take this structure and come up with the equilibrium configuration based on the minimum energy criteria and using the Boltzmann distribution. But then once you are in the equilibrium state, now you are looking at equilibrium radius for different kinds of bonds that are formed in between. So, there could be different kinds of bonds. If you look at the previous slide, then you can look at 1 and 2 and 2 and 3. So, these are the bonds which are linear bonds. So, there is no issue with that. You know the bond length, and if you know the spring constant, you can calculate that. But between 2, 3 and 3, 4, there is an angle. So, you are looking R 2, 3, R 1, 2, R 3, 4, and the angles between them which are in the plane and the angles which are out of the plane. So, those are the in the plane angle is theta, out of the plane angle is phi. So, once you understand that, then you know that the whole intramolecular interaction has k, these are the spring constants, and then you are looking at the bond length. So, this is a simple spring constant Ij. This is the bend angles bending between. So, we are looking at theta, which is in plane, and now you are looking at phi, which is out of the plane. So, with that understanding, we can look at hydrocarbon potential. These are empirical potential to describe interaction between molecules. So, you have inter and intra. So, intermolecular is those bond lengths and bond angles. Intra is between carbon and carbon, and that is where you can bring back your ideas of Leonard Jones, where the carbon-carbon interaction could be happening in intramolecular way. So, that those two atoms are interacting through Leonard Jones, but between carbon and hydrogen chains which are formed around that carbon, that could happen as intramolecular forces. So, bonding potential is Kr Ri minus Rj square, bond angle Ka. So, these are all different force constant. Two body Leonard Jones plus charge interaction is for intra, and intermolecular are all these different dihedral angle and their force constant. So, if you look at a commercial package like amber, you can see all of these things have to be defined, and with that you are able to sample the potential energy surface as you see in the picture here. So, now we are looking at bond rotation potentials, and you can see the rotation, and so these rotations are happening with the different pair 1, 2, 3, 4 that we looked at, and rotate along the bond. So, along the bond there is a rotation. Then you look at the both angle, bond and stretching, all three together. So, this one is stretching. So, the bond stretching happens here, and this is where the bond bending is happening with theta in plane, and other is the out of plane, which is this one. So, understanding these interactions are very important, because that is how you are now able to look at a system which is very prolific in the biological system and almost is a substrate for all the biological activities, water. So, we are now going to look at water potential and see how we can understand intra and intermolecular forces in that. Thank you.